In the last lecture, we have discussed about different measures of uncertainty, and we have seen how probabilistic reasoning helps in reasoning under uncertain circumstances. Today, we will discuss about a novel technique called fuzzy reasoning, which is based on fuzzy set theory and consequently fuzzy logic. This notion of fuzzy set theory was proposed by Lotfi-Zadeh. Now, we have already seen that in our day-to-day conversations and communications, we often use terms, words which are rather imprecise in nature. It rained heavily. Now, what does that term heavily mean? Okay. The boy is very strong. How strong is heavy strong? The color of the curtain is more or less red or reddish. Now, these things, these terms do not find a direct mapping to any quantification like a number. When I say the boy is good, the boy is very good, then I obviously do not immediately imply that the boy is 7 good or 8 good or something like that. Now, these sort of terms are very useful in our day-to-day communication, but certainly poses a difficulty when we try to compute with these things. Now, fuzzy reasoning, fuzzy set theory and fuzzy logic deals exactly with this particular thing, how to handle such imprecise scenario. So, today we will be discussing about fuzzy reasoning, and if I just show you this picture on the left side, who is this? It is more or less, you will all of you will agree that it looks like Abraham Lincoln, but it is more or less like Abraham Lincoln, right. Now, how is it that we can certainly identify that okay, this is the figure of Abraham Lincoln? The complexity of the decisions from such subjective inputs, decision making that we do in our mind is really intriguing, and often we do not really understand, and often we cannot model them in quantified manner. Now, we have already seen what is meant by stochastic uncertainty, that is the cases which we handle with probability theory, like the probability of hitting the target is 0.8. That means, we have carried out a number of experiments, and based on those experiments we have seen that in 80% of the cases we could hit the target properly. But there is another category of uncertainty which is called lexical uncertainty. Now, what is meant by lexical uncertainty? Lexicon means the dictionary or the set of words. So, the uncertainty that creeps in from our usage of day-to-day words, that those are subjective, sometimes they are ambiguous, and often they are imprecise. So, for that different types of uncertainty creep in. For example, we use tall men, hot days, stable currencies. Now, you see everywhere tall, hot, stable, what do they really mean? Stable currencies. Will probably have a successful business year. Now, here the term that we have used probably is again not very stochastic in nature. It is just our guess, our feeling that we will have a successful business year. Now, what do you mean by successful? When would you say that your business has been successful in this year? This word itself is very imprecise in nature. The experience of expert A shows that B is likely to occur. Now, again B is likely to occur. What degree of probability would you assign to the word likely? Okay. That is really imprecise. Expert C is convinced that this is not true. Now, here you see convinced and it is likely, these are two different terms. Convinced means he is sure, so the certainty is 1. Now, again, in order to bring out the difference between probability and uncertainty in terms of the imprecise aspects, fuzzy, vague aspects that we are talking about today, we can look at this sentence. A person suffering from hepatitis shows in 60% of all cases a strong fever. That means, in 60% of all cases, so this is rather probabilistic, but what is imprecise? Strong fever. When do you call a particular fever or temperature to be strong? In 45% of all cases, yellowish colored skin. Okay. What tinge of the skin would you say yellow? Which tinge will you say to be surely yellow? Which one is more or less yellow? Which one is yellowish? So, this term yellowish is again imprecise and vague, and in 30% of all cases they suffer from nausea. Now, you see 30% of all cases suffers from nausea. So, the symptom nausea is present in 30% of all cases. So, this part is certainly probabilistic, whereas this first part, a person suffering from hepatitis, shows in 60% of all cases. Now, this is probabilistic, strong fever is again imprecise. So, that is fuzzy. In 45% of all cases, yellowish colored skin, this is also a mix of probabilistic and fuzzy. So, here we will show you a conventional Boolean set, the conventional set. Say if we have strong fever as a set, then now this slide has been taken from another source. So, these measures of temperature are not like the ones that we do in India, but in West they measure the temperature in degrees Celsius, body temperature. So, here you see 40.1 degrees Celsius is certainly strong fever, 41.4 degree strong is strong fever, 42 is strong fever, and 39.3 is strong fever, and 38.7 goes absolutely out of this set. So, this is not a strong fever, but the question remains that when I say 39.3 to be strong fever, why should not I consider 39.2 to be strong fever as well? And if I consider 39.2 to be strong fever, why should not I consider 39.1 or 39 or 38.9? In that way 38.7 also to be strong fever. Can I make such a crisp boundary? In many cases where we use such terms, it is very difficult to make such a crisp boundary. On the other hand, here in this diagram you see that the boundary is not very crisp, it is gradually fading out. So, at the core it is certainly strong fever, and as I go out it is becoming gradually faded, and so it is becoming less and less of an element of strong fever. And this is a critical term that I have used. It becomes less and less of an element, gradually its belonging to the set is becoming less. Here either you belong to an element belongs to the set or it does not belong to the set. It is a binary decision, yes or no. On the other hand, here we can see that 40.1 degree is inside the set, 42 is inside the set, 41.4 is also inside the set, 39.3 is slightly in this shaded region, and 38.7 is even further. So, in order to capture this scenario, fuzzy set theory was proposed. Okay. Now, fuzzy set theory, always there is a very there is close correspondence between a set and logic, because in logic we use predicates. So, when we say a particular set, that say we take any particular set say a set X in which there are elements A, B, C, then obviously we can say that A belongs to X, and suppose D is outside the set, D does not belong to X. So, this can also be expressed as predicate that belongs A X does not belong D X, right. Might be D is belonging to another set Y. So, belongs D Y. So, this belongs is a predicate, and therefore, this set belongingness of a set or definition of a set immediately maps to predicate. So, from set we can always come to predicate logic. All right. So, now we say that fuzzy logic deals with qualitative information, the information that is qualitative. We do not have always quantitative figures to deal with it. This is more realistic than predicate calculus, because in real life we need to deal with qualitative statements. Say here is an example from a chemical plant. We often use rules like this: if the temperature is moderately high and the pressure is medium, then turn the knob slightly right. Okay. Now, if the temperature is moderately high, this part, say earlier we had dealt with predicates like say if age of Tom is 50 and weight of Tom is 20, weight of Tom is 65. Here you see everything was precise, but here we are using if temperature is moderately high. That means what? If I write in this way, if is temperature something like moderately high. Now, this is no longer a precise term. So, here we are facing a difficulty, and but it is nevertheless more realistic, and the pressure is medium. Now, which pressure is medium? Turn the knob slightly right. How much angle? What angle would make it slightly right or slightly left? Okay. So, we use this sort of terminologies. So, dealing with precise numerical information is often inconvenient, because it is not very suitable for human beings. I mean, if you ask the expert to say, well, tell me what exactly the pressure should be, he will not say that, because he has got a feeling that if the pressure is medium, turn the knob slightly right, exactly how much? Well, I will not say 42.7 degree or 4.56 degree, not to that precision. That is more realistic, and so here are some more examples which deal with such imprecise statements, and these are coming, these impreciseness are coming from the power of language, linguistic variables these are called, language allows us to express, natural language I mean, allows us to express in a much more comfortable way. And in order to model it in the quantitative world, often we have to translate that into a quantitative statement, and that translation is often artificial. So, we are trying to be as natural as possible in this case. So, weather is sunny today. Okay. What do you mean by sunny? It is very cold in the Himalayas. Rich people have a lot of worries. Now, when would you call a person to be rich? When would you call a temperature to be very cold? All these things are imprecise. Now, fuzzy set differs from crisp set in terms of membership. In the case of a crisp set, okay, say whenever we look at a crisp set, any particular set X which consists of 1, 2, 3, 4, 7, 9, then either X, any of these elements either belong to this set or it does not belong to the set. So, for any element, so if I take a superset, a universal set, a set of all integers, okay, this is a set of all integers. Now, given any u belonging to this, so if I take any integer, either that will belong to this x or it will not belong to this x. So, the membership of this in the case of a crisp set, membership of u is in x is either 1 or 0. That means belongs to or does not belong to. There is nothing in between. Whereas, in the case of fuzzy set, the thing is different. So, we will use the same notion of membership, but if I now change this set to a fuzzy set, then let us see how can we talk about it. Okay. Suppose now I say that it is a set height which is 5 feet, 5 feet 2 inches, 5 feet 4 inches, 5 feet 5 inches, 5 feet 6 inches, 5 feet 8 inches, say this, and I define a set medium height. Now, this is my universal set U, okay, and you see this is a crisp set. This set is a conventional crisp set. For example, 6 feet is not in this set and in this discourse, okay, 5 feet 5 inches is there. Now, medium height, what would you say? What would that set be? Will 5 feet 4 inches be in medium height? Suppose you say it is there. Then 5 feet 5 inches you think also in medium height. 5 feet 6 inches will also be in medium height. 5 feet 8 inches will also be in medium height, and you say that these two will not be there. Fine, these two are not there, these are outside the set. All right. So, I have taken these 4, but the question is, if you consider 5 feet 4 inches, is its belonging to medium height as strong as 5 feet 8 inches or 5 feet 6 inches? Probably no. This has got a weaker belonging, this is 5 feet 4 inches, and this 5 feet 5 inches has less weaker belonging, whereas 5 feet 6 and 5 feet 8 certainly belong to this set. So, the degree of belonging of these elements have to be requires to be specified, but this was not the case when we are discussing about crisp set. So, we can define as the thing that I was saying, say the example of a set 2, 3, 5 A, B, C, and suppose this we have got a universe of discords. Now, 1 belongs to S, 1 does not belong to S, A belongs to S. So, that is a crisp set, but if we try to generalize it, in the case of fuzzy set, in the crisp set the membership is either 1 or 0, but in the case of a fuzzy set, the membership of an element x in a set S is no longer 0 or 1, rather mu s x is between 0 1, both are included. All right. Now, this requires a little bit of explanation. All right, this mu s. Say I take the example of medium height here. Now, I have got an element x belonging to a set, universal set x. For example, some element x belonging to the set height, which was a crisp set, as I was showing. Now, I am defining a fuzzy set, say medium height or medium, which will take, which is a subset of this universal set height or x, this thing, these two are the same thing. Now, when I define medium, say I can say that 5 feet 4 inches has got a belonging of 0.3 in this set. 5 feet 5 inches has a belonging of 0.5. 5 feet 6 inches has a belonging of 0.8. Now, these are rather subjective, and this is coming from the user's notion, your notion of medium height, and 5 feet 10 inches is certainly medium height. So, this set what we have actually done is, along with every element, okay, every element x, I have put in a membership function mu of this element, particular x, element x, in the set fuzzy set medium, and that is followed by that particular value of x. Just as in the case of crisp set, this mu x in a fuzzy set, say medium, would be either 0 or 1 in the case of crisp set, but for fuzzy set it will be in the interval 0 and 1, it can be 0, 1 or any number in between. So, this is mu of x in the set M, say, where M is a fuzzy set. This means membership of x in M. This is also known as degree of membership. All right. So, this is a generalization of the conventional set theory that we know. So, here you can see that mu in a set S 1, crisp set S 1 is a predicate which denotes x to be an even number. Now, so here is a final definition that I was trying to explain. Boolean or crisp set A is a mapping for the elements of S to the set 0 1. That is, A is mapping elements of S to 0 and 1. So, a characteristic function for a fuzzy set for a crisp set is 1 if x is an element of the set A, okay, 0 if x is not an element of the set A. On the other hand, let us look here, fuzzy set F is a mapping for the elements of S to the interval 0 1. So, characteristic function is a membership function of x belonging to F that will lie between 0 and 1, where 1 means full membership, 0 means no membership, and anything in between, for example, 0.5 is a graded membership that is telling us what is the degree of its belonging. So, we can say that mu s x, again x is an element of the crisp set S, and this is also a predicate, is a membership, it is also called, it is a membership predicate. All right. Now, let us give some examples. Fuzzy sets and concepts are commonly used, like say John is tall, Ravi is smart, Sajani is happy, the room is hot. Now, for example, the crisp set tall can be defined as x. Where from x is coming? X is coming from the set height, and we say that all the x which are greater than 1.8 meters will belong to the set tall. So, tall is a set consisting of all x where x is greater than 1.8 meters. Now, what sort of set is this? A crisp set or a fuzzy set? If I define in this way, then it is certainly a crisp set, because any number, any height that is greater than 1.8 meters will certainly belong to the crisp set, to the set tall, and if it is less than 1.8, then it will not belong to that set. Fine, but such crisp set, such definitions of tall puts us in trouble, because what about a person of height 1.79 meters? What about 1.78 meters? What about 1.52 meters? Obviously, logically you will think that 1.8, if it is in the set tall, we should not be so much cruel to 1.79. We should consider that to be also tall, but not certainly 1.78 should therefore also be in tall, but then how would I distinguish between somebody who is 1.8 and somebody who is 1.78? Now, so the crisp set notion does not allow us to do that. On the other hand, let us look at this. In a fuzzy set, a person of height 1.8 meters would be considered to be tall to a high degree, and a person with a height of 1.7 meters would be considered tall to a lesser degree. Therefore, I can define a function to describe the fuzzy set. For example, let us look at this set. There is a typical graph. All right. What is this? The x axis of this graph? Probably that is not very visible. I will just draw it again. So, on this side of the graph we have got height, and on this side we have got the membership. Okay. Let me work it out. We are having two axes. On this axis I plot the height in meters. and this height is coming from the crisp set, that is the universe of discourse. Now, it may be say 1.2 meter, 1.4 meter, 1.5 meter, 1.6 meter, 1.7 meter, 1.8 meter, all right, in meters. On this axis, I am plotting the membership of a particular height, say some height h, in the set tall, because I am going to define that set tall. Okay. So, in tall, the graph may be something like this. Let me select another color. Over here, up to this I am not considering them to be tall at all, but then it is going up, and here, sorry, this this should saturate out to 1, it is saturating to 1. So, this membership is 1.0, here it is say might be 0.9, 0.8, 0.7, like that it is going on. So, if I now here this graph therefore is mentioning my subjective interpretation of the concept tall. Now, if I come across some person who has got a height 1.7, then simply I will project this over here and we will say, well, its membership, yes, you also I will give you a place in tall, but with a membership of 0.8. If somebody comes with 1.6, then I will also give him a place and maybe with a degree 0.4. If 1.5 comes in, he is also not deprived, he will get probably 0.1, and below that everybody is getting 0 or something. Now, this notion, this is my definition of say one particular definition of tall, but again now let us say I am trying to select a basketball team, and I have been told that you should select only tall people. In that case, my notion of this fuzzy set I may like to change, because I may like to have again the same axis on this side I will have height again and say 1.8, 1.7, all the same figures are here, and on this side I am putting in mu tall u or anything h, if this is u, whatever. Now, I can redefine my fuzzy set in a different way now, because I am rather strict about the height. So, maybe I will make my curve something like this, I will make a very slow and then I will make it 1. So, somebody who is 1.8 will certainly get a membership 1, somebody is 1.7 will get a very low membership. All right. The earlier curve was a little different, the earlier curve was little flattened, something like this. So, there 1.8 also got a membership, 1.7 got a quite some membership, but when my purpose is to select a basketball team, I will go for a steeper curve like this. So, that is what my notion of tall is when I select the basketball team. So, that is how the fuzzy sets are defined. Okay. Now, say here, say a number, here are some numbers, and I want to say give me a number which is about 600. What do you mean by that? Okay. How much money would you need? I would need about 600 rupees. Now, what do you mean by about 600 rupees? Now, if I want to capture, conceptualize this notion about 600, then I have to define this about 600 to be a fuzzy set over a crisp set of these numbers 500, 600, 700, etc. And the shape of the curve will be like this, because for 600 certainly it is the membership 600 has a membership of 1 in the fuzzy set about 600, whereas 599 will have a very high membership, maybe 0.97 or something here. 550, is it about 600? Well, I will go here and say yes, around 0.5, it is about 600, its membership in the fuzzy set about 600 is 0.5. 520, its membership is around 0.2. What about 650? Its membership is again 0.5. So, here this would be a very natural curve of distribution of the membership to the fuzzy set about 600, right. Here say I'll give another example about conceptualization. Say I am defining a set. Now, I am just posing a rather philosophical question to you: how true is true? That means, I say, well, what he said is true, okay? Or say I say 550 belongs to the fuzzy set about 600, this statement is true. Now, you see, in predicate logic we were saying that a predicate is found to be evaluates to true or false. There our concept of true was 1 and the concept of false was 0. Now, how true is true? 550 belongs to about 600 is true. I make this statement. Now, I say about this truth, should I give 1 or what? Now, we have seen in the earlier diagram that 550 has got a membership mu of 550 in about 600 in that fuzzy set was 0.5. Now, a membership of 0.5, that means its belonging was 0.5 to the degree 0.5, then it belongs to about 600. Is it true? Now, I can define truth now also in fuzzy term, where here I put in say mu of say about 600 and the different values of this thing. So, say, and here is the membership in a fuzzy set. I define true to be a fuzzy set, mu true of say I say this is V, right. Now, this 0.5 had was somewhere here. Now, if I define the truth fuzzy set to be something like this, then 0.5 belonging degree of belonging 0.5 in my notion of truth, I can say this is also say this curve is such that it is something like 0.6, something like 0.6. But you may be even more even stricter than me, and you can say, well, this is not my notion of truth. My notion of truth is something different. My notion of truth is this. My notion of truth is very steep, or rather this is dilated. Say your notion of truth is this, all right. In that case, in your notion of truth, the statement 550 belongs to about 600, how true would it be? It will map here and its membership will come to say 0.4. Whereas, another person may be a bit more lenient, because he feels that any membership that is more than 0.2, then I can say it belongs to a particular set. So, he will go for this curve, and the same membership of 550 in about 600 is 0.5 will be taken up here, and it will evaluate to say might be 1. So, in this way the notion of truth can also be modeled in fuzzy set. Here is another description of a fuzzy set. On the x axis we have plotted height, on the y axis we have plotted the membership of the different heights in different fuzzy sets. Here we have defined three fuzzy sets, one is tall, one is medium, one is short. Now, the curve for short, if you follow, is coming like this one, that is height of 30 centimeter is short, certainly short, but height of around this point say 50 centimeter is short, but after with membership 1, but somewhere here height of say 80 centimeter, its membership in short is 0.7, height of 100 centimeter, its membership in short is 0.2, like that. Whereas, medium height, the distribution is something like this. Okay. Whereas, tall, the distribution is something like this. So, you see we capture the different notions. Now, you can ask that where from am I getting these figures? These figures, there are different ways of doing it though, but these figures are representing your conceptualization of a particular term. I say you say that the room is hot. You are saying it from a feeling, and your feeling may differ from mine. So, up to what room temperature would you really tolerate, and after that you will say it is becoming hot and the AC should be turned on. That is your notion. So, based on your notion of the term, you have to find a particular distribution of the membership function, membership values, and that will define the fuzzy set. Say here again we are revisiting that strong fever case. In conventional Boolean set theory, it was like this, and in fuzzy set it is represented in this way. Now, we can define say discrete definitions. We can say strong fever. If I say strong fever 35 degree, these are zeros, these are discrete definitions, and I can have a continuous definition like this. Discrete definition is that 43 degree centigrade membership in strong fever is 1, 42 degree centigrade's membership is 1, 41 degree centigrade's membership is 0.9, 40 degree centigrade is 0.65, so on and so forth. So, I have discretely taken up all the values, but in this way if I want to tabulate, it will be difficult, because I will have to, since it is a continuous domain, I have to write for 35.5 degree, 35.4 degree and everything. If I select some discrete values, I can do it in this form, and I can represent it in the form of a table. Whereas, you see this is the continuous definition here, this is the curve going up, all right. So, we can take any particular value and come to this point and find out the membership. 41 degree membership is somewhere here, it is 0.9. So, 39 degree its membership is somewhere here, and 38.9 degrees membership somewhere here. So, since we have to work with computers, how do we describe a set? How can we describe a set? A set can be described in two ways. One is by extension, or by intension. Okay. Say even in the case of a crisp set, conventional set, we are familiar with these notions that I can either extensively enumerate that my set X consists of 3, 7, in that way I can go on, all right. That is one sort of definition. Another sort of definition is, say I can define a set Y to be Xi, all X, such that for all X, or say such that X is greater than 5, all right. That means, I am defining a set 6 and onwards, right, X is greater than 5, if I say only integers 6, 7, etcetera, in that way. So, this is an definition by extension and this is an implicit definition. Now, this is also the case in case of fuzzy sets. So, we can define S2 to be a set of tall people, okay, and we can put in a membership to this. Now, in the case of fuzzy set, we can define it in this form, say tall, look at this, 1.0, its membership in tall is 0, 1.2 its membership is 0, 1.4 its membership is 0, in that way I am going on, all right. Now, in some books you will find that this comma is replaced by this plus. Now, this plus is not addition, this means union. So, I am talking of a set where this element union this element union this element. So, all these things are together. Now, how do we represent a fuzzy set, say in a computer? Say I am defining a set, say there is some age, I have got a set age, where age is say 5, 10, 20, 30, 40, 60, 80, all right. Now, I can define a number of different fuzzy sets, also I can represent them in the form of a table. For example, I define one fuzzy set child, okay, or young. All right. And here I put in say 5, 10, 20, 30, 40, 60, 80. Now, I put in the memberships that 5 is certainly young, 10 is certainly young, 20 is certainly young, 30 is say 0.6, 40 is 0.5, 60 is 0.1 or 0.01 and 80 is 0. So, this is a table using which, so I can also show draw the same thing as a, this is my definition of fuzzy set young. So, here it is age and my values are here 5, 10, 20, 30 like that. And what is that curve then? These are, here it is membership. So, for 5, 10, 20 the value is 1, and after that it has come to 0.6, and after that it has come to 0.5, and then there is a sharp fall. This is our young. The same thing, this is the graph that is representing young, and the same thing can be represented in the form of a table. That is one way we can represent a fuzzy set in a computer. Now, similarly, I can define another fuzzy set, say old, where obviously 5 is not old, 10 is not old, 20 is not old, 30 is not old. Here you say 0.2, 60 is 0.5, and 80 is say 0.9, 90 might be 0.1, 90 might be 1. So, if I describe this fuzzy set, then also I have actually mapped a particular curve. What is this curve? So, if this be the age here and the membership on this side, these are all zeros, and after 40 it is 0.2, then 0.5, and then 0.9, something of this sort. Now, this curve can be mapped to this form of a table. So, the curves that we are showing you till now can be represented in the form of a table, therefore, it is amenable to be represented in a computer. Now, I leave over here to you to similarly fill up another set, which I will not do here, and that will help you in understanding. Say adult, you want to define a fuzzy set adult, just put in the membership values here, all right, and that will define your notion of adult. So, in that way, this is one way fuzzy sets can be represented in a computer. So, here, so we always describe these things in terms of some profiles, and these profiles reflect our conceptualization of the fuzzy term like tall. So, here is a profile of different heights, and this is my notion of tall. And what are my axes here? This is the membership 1, this is the membership of h is any variable on this axis, membership of h in the fuzzy set tall. This is a profile of tall. Okay. You must have realized this by now. Now, there are different shapes of profiles. How do we get them? Shapes of profiles are obtained from experiments and expert judgment. We sometimes carry out some statistical experiments, like I fill up a questionnaire and go to say 1000 people and say, would you consider 6 feet to be tall? Would you consider 5 feet 8 inches to be tall? And then we see how many people have really said that 5 feet 8 inches should belong to tall. Based on that, we try to put in some measure of membership. But however, this profiling all said and done is somewhat vague, and this has to be done by the expert who is, or the user who wants his notion, his or her notion of fuzzy set to be captured. So, there are different types of functions. Here is another type of function which is called the S function. So, this function, this curve can also be expressed as, you see, for any a, for any x less than a particular value, it will be 0. Between two patterns, two values, say 2 points a and b, it will be computed by some function. Between two other points, it will be computed by some other function, and after that it is 1. This is one type of profile. So, this profile can be represented as a table or can be represented as this function, which can be computed using a procedure in the computer. Similarly, here is a very interesting thing. Say I say that close to a number which is close to a. Now, obviously, conceptually it is something like this, right. A is certainly close to a, membership 1, something which is in between these 2 points, if it is at B either plus on the positive side or negative side, it will be 0.5. Anything in between will have a membership in between. In that way, we can have a bell type of curve, and this is another way the membership functions can be represented. I would encourage you to find out a mathematical function, an expression to represent this sort of a curve close to A, so that we can also use it. We can of course tabulate it, but we can also use it for computation as a function, as a procedure. Now, we stop here. In the next lecture, we will continue from this point onwards and see how these notions can be effectively applied in fuzzy reasoning.